So today I'll talk about the neural network landscapes. And let's get started. The talk will be largely based on our ICML 2021 paper. So the big question today for me is, how much overparameterization is sufficient? In literature, we already have a well-developed theory for infinitely wide and very large width networks. The analysis usually relies on the neural tangent kernel or mean field techniques. And with either techniques, optimization with gradient flow probably converges to zero loss. This is well established. However, the results are vacuous if the training data set is large. So today, I'll present an average case analysis in search of having a theoretical framework that is relevant for practical size with networks. So we will see an example of this today. And there are already some example case average studies of complex landscapes. For example, spherical spin glasses or spiked matrix tensor models. So we'll get inspirations from these models, but we will apply a new analysis for neural networks. So our particular goal today is to quantify the roughness in neural network loss landscapes. So let's start with Glassy Landscapes again. So in complex landscapes literatures, Glassy landscapes are typically, there's an exponential explosion of the number of saddles. Again, I'm using the example of the spherical spin glasses. Or we can also say the roughness is the number of saddles or the number of explosion rate of the saddles. And so typically, these landscapes are very high dimensional. But just to have some sort of intuition, I'm showing you a two-dimensional picture here that looks rough in the sense that there is a lot of saddle points in between these mountains that we are seeing. But we are interested in overparameterized neural networks today. And the number of components of global minima manifold also scales for neural networks, which doesn't happen in the complex landscapes. So to study roughness, we have to study the number of saddles normalized with the number of global minima. And here I'm showing an example of a smooth landscape in 2 dimensions. It's totally a cartoon picture for some intuition. So I'll show that in mildly overparameterized networks, we have a rough landscape, whereas for vastly overparameterized networks, we have a smoother landscape. And moreover, roughness gradually decreases with overparameterization. And how am I going to do it? I'll use some symmetries. So we'll focus on 2 symmetries preserving the network function. So on the left, I'm showing a 2 layers network that has width R. So for the sake of today, I'll use 2 layers networks, but the approach generalizes for multiple layers. So we have a width R network with incoming vectors denoted by W1, 2, 3, and the outgoing vectors by AI. And I'm showing you here the network function, which is denoted by f and n, applied to an input x. And its output is equal to the summation of its neurons, which we see here. So the first invariance we consider is neuron splitting. Say I'm taking the green neuron, and I split it into 2 pieces. How do I do that? I copy its incoming vector, W1, and split its outgoing vector into 2 pieces. And I'm keeping the summation the same, so that it produces the same neuron as before, so that the network function is the same. So this is the first invariance we consider. And the second one is the zero neuron addition. How am I doing it? Now I keep all the neurons. I'm adding now new types of neurons, which are colored in gray here. So the incoming vectors are arbitrary. And the outgoing vectors are such that they cancel each other. So overall, I'm adding a 0 neuron. So it doesn't change the network function. Okay, here there's a key observation for the first type of invariance. That is that the neuron splitting preserves also criticality. And this was first discovered by Fukumuzi and Amari in 2000, who are also from Japan. But I'm not sure if I'm lucky enough to have them in my audience. And for the second type of invariance, they didn't study it back then. And because it doesn't break, it does break criticality. So it's going to be only relevant for the global minima manifold, but not for the saddles. And what we are going to do today is that we can apply these symmetries over and over again. So I added one neuron in the first picture. Now I'm adding another green neuron by splitting it again into two pieces. So I have the same network function, and criticality is still preserved. And I can also split another orange neuron. It is the same story. So we'll consider arbitrary duplications of neuron groups. And so we will have two parts to study the critical manifolds and the global minima manifold. And then we are trying to build up towards the last part, where we will show that roughness decreases with overparameterization. So let's start with the symmetry-induced saddles and the number of manifolds. So here we take an irreducible critical point. And irreducible here is just to say that all the neurons are different from each other. So they have the same color in my representation. They have different colors according to my representation. So we take an irreducible critical point from a network with width r. Now we consider a larger network that has a larger width, which I will denote by m. So in the larger network, I'm constructing a set of affine subspaces. So each affine subspace has the same loss, and at least dimensionality m minus r. And the number of such affine subspaces can be represented by this G number. So we will take a closer look at this G number. OK, so let's consider the simplest case first. What if I just add one neuron to the network? So now I'm going to study this number, G r plus 1. And I want to explicitly compute it with you as an exercise. OK, so I have r neurons to start with. So I have to choose one of them to split into two pieces. So that gives me an r choose 1 factor, which neuron to split. Then I ended up with r plus 1 neurons, but two of them are identical to each other. And the number of permutations among these neurons is r plus 1 factorial divided by 2 factorial. So I'm lucky in this case, because I can explicitly compute the G function. But for the general M case, it is actually a quite complicated problem, which we'll see in a moment. Oh, I want to comment on this picture here, too. Like here, we see distinct affine subspaces, because in this case, all affine subspaces are actually lines, because I added only one neuron. And they are disconnected from each other, and they are permutations of each other. Let's go to the case with general M. So the counting problem becomes equivalent to arranging r incoming vectors into m slots. And the second layer is going to follow accordingly. So how do I do this counting problem? I'll reformulate it as another counting problem. So we start with a width r network. And we want to map r, a set of r elements, into another set of m elements in a surjective manner. And this, as we realized after the publication of the paper, this brings us to the domain of enumerative combinatorics. And this is a well-studied number, and it's not so easy to study. So that it is a number of surjective functions, basically. But it's not what we are interested in, because we also want to consider the different colorings of this partition. So that's going to give us an extra r factorial factor. So the first number comes from enumerative combinatorics. That is this special representation. It's called the Stirling number of the second kind. And we get an r factorial factor. And I'm just plotting here this G number for some cases. For m equals 10 to 30 is a function of r. And I see that it's always unimodal. And this, even though I changed the m, the peak happens at the same ratio for r over m. So we were curious about this, like where this, is this a universal constant, or can we study this analytically, like this behavior of the G functions? And it turns out it was a problem that was Tim Govers, who is a Fields medalist, was asking this question on the forum, and Terence Tao gives the answer. So it happens it wasn't an easy problem. And indeed, the answer is 1 over 2 log 2 asymptotically. And in the first plot that I showed you, we see that it kicks in for finite sizes too. And the vertical line that I drove is also at 1 over 2 log 2. To summarize the section, so for all those critical points that originated in a narrower network, we call them symmetry-induced critical points. An irreducible network of a network with width r induces an explicit and huge number of manifolds in the landscape of the larger network. So let's move on to the global minimum manifold. So we have a similar theorem. Just that. Yeah, sorry. Now we just have an R star, and it's not on my slide. So we assume that there's a teacher network at this point that has a width R star. So this network achieves zero loss, and all the networks wider than this are going to be called overparameterized. So now we consider an overparameterized network with width M that is larger than R star. So then we are able to construct a set of affine subspaces of zero loss points, each with dimensionality at least M minus R star. So the number of such affine subspaces is not the G number anymore, but here we are representing it by this T number. That is the G numbers plus some additional factors. This additional factors comes from the zero neuron addition groups. It is the second invariance that makes this number bigger. And I want to apply the theorem in a Veritoi setup with a teacher with 2 neurons and a student with 3 neurons. And if I compute this T number, it gives me 12 affine subspaces that are connected to one another. And in this case, I can even draw it like as a manifold of. So I'm always counting the number of components of the global minimum manifold. The manifold itself is 1, and it's a connected manifold. And here I'm referring to a lot of cool works who studied the connectivity of the global minimum manifold, in the sense that they take 2 zero loss points and they find a path connecting these 2 points. And on the path, the loss does not increase. That's the idea. And here we are able to show that there's a higher dimensional connectivity as you overparameterize more and more, because we have this lower bound on the dimensionality of the affine subspaces. And the assumption came a little bit later. Sorry about that. And now the question is, so I showed you this construction of the zero loss points. It gave me an expansion manifold and a space of global minimum manifold. But did I consider all the zero loss points of the overparameterized network, or are there other zero loss points? And it turns out if I assume that the teacher network is unique up to permutation, and that the input distribution has full support, so it's not a discrete distribution and it has full support, for example, it could be a Gaussian distribution. In that case, the answer is positive, but I have to also assume that the activation function does not have like secret invariances. For example, ReLU, you would get a scaling invariance immediately, and I'm not considering such things in this manifold. And those are the conditions on this on the first part of the theorem, basically. So to summarize the section, for full support input distributions, all zero loss points are identical to the teacher network, up to neuron splitting and zero neuron addition. And the global minimum manifold is composed of an explicit and huge number of affine subspaces. And finally, we will compare the scaling between the saddle manifolds and the components of the global minimum manifold. So that brings us to the third part. So to compare these quantities, we have to simplify the setup a little bit, because so far all the principle applies to general neural networks. So for that, we assume that there is exactly one minimum up to permutation in the underparameterized networks. And I'm putting a cross for each one of these minimums on the plot. And that there are no further irreducible critical points that we didn't account for in the overparameterized networks. So I have also a teacher of width R star. Now, if I consider a student with width M, this student will have a lot of critical manifolds coming from underparameterized networks. So G1M is the mapping of the 1 neuron minimum to the network with width M. And I map from all the underparameterized networks. So I'm collecting the saddle manifolds coming from all the previous networks. So that gives me all these G numbers. The number of components are the G numbers. And there is a global minimum manifold. So the roughness, now I can explicitly, quantifiably express the measure of roughness. And first I'm going to plot it for a particular value of R star, let's say 30. And as we see, this roughness value decreases with overparameterization. But it's not unique to R star equals 30, because I have some limits. So for the mildly overparameterized case, when M is just a little bit larger than H, so the teacher width goes to infinity to make this limit work, but the student has just a few more neurons, then the saddle manifolds are polynomially larger than the number of components of the global minimum, polynomially larger. And for the best case, I can upper bound this quantity of roughness by an exponentially decaying factor in the student width. So it has to go down to 0 exponentially fast after some point. So this gives us two regimes, mildly overparameterized and vastly. And what happens in the deep case, because this is a simple principle coming from the permutation symmetry, I can apply the same principle to all of the hidden layers of the network. And that's going to give us an exponential factor in the number of saddles and global minimum. So the roughness measure also gets exponentiated. And I'm going to show some empirical results. So far, we studied the critical points of the neural network landscape. Does it have any implication for the dynamics? And here's a very simple setup with two-dimensional input, a teacher with 4 neurons. And I'm training a student with 5 neurons or 45 neurons with typical initialization. So for the 5 neuron student, it turns out that the 14 out of 50 initializations fail to find the global minimum. Whereas for the vastly overparameterized student, all the initializations converge to a 0 loss. Okay, so this is a slightly less toy, but still a toy model. We have a deep teacher with 3 hidden layers now. And we go to the overparameterized students with 5 neurons in each one of the layers. So all the initializations fail to find a 0 loss solution in this regime. And for the vastly overparameterized student, all of them converge to a 0 loss solution. Same story, but a bit more pronounced. So we will have one more experiment now on the amnes data set. So we are fitting a network with 30 neurons to learn the amnes data set. And we change the labels into soft labels predicted by this teacher network. So the teacher now can achieve the 0 loss because we are following the predictions of the teacher. And then we train an overparameterized student until convergence. And this is the result. So we have 50 or so students for each one of the overparameterized networks. And the dots represent the losses that they achieve. So what do we see here? For mild overparameterization, they don't go so far down, although they could, because we know that there is a manifold of global minima points that is connected. We constructed it just before, but they are not able to find it because the landscape is super rough. And as the roughness gradually decreases, the fractions of success is also increasing with overparameterization. And OK, so here I'm going to be a little bit shaky, but if I plot the 2 log 2 factor just here, you see that just before 2 log 2, we see that the first cases of convergence to 0 loss. And then after that, there is always a non-zero probability of converging to 0 loss. But it's not a sharp phase transition, or we don't know it's a general phenomenon. At the moment, it's a speculation. So overparameterization not only decreases roughness, but also removes some failure modes in the landscape. And for the conclusions, so we worked out that the neural network landscapes exhibit families of symmetry-induced critical points, which are represented in the first plot. And we go to the overparameterized networks and study their global minima manifold. We find that the 0 loss points form a certain number of affine subspaces that are connected to one another. This is French. Should I say yes? Oh, no, it's not. It doesn't ask me. They don't see it. So the roughness decreases with overparameterization, combining these 2 results. And we observe 2 extreme regimes. The first one is the mild overparameterization. And we prove that the roughness is polynomially large in the teacher width. And empirically, we show that it's a rough landscape. So, I mean, we show theoretically that it's a rough landscape. And empirically, we find that it's difficult to find the 0 loss point. And for the second extreme regime, that is the vast overparameterization. So we show that the roughness is exponentially small in the student width. So it's a smooth landscape. And empirically, we show it's easier to find a 0 loss point, which is also consistent with the literature. Here are the references, and thanks for your attention.
Questions for Berfin?
Sorry if I didn't. Should I stand or? I didn't. Sorry if I didn't understand this, but I just wanted to ask you quickly. So when you when you get a deeper network, so when you vary the width, you increase in parallel the width of all layers at the same time, right?
Yes, in the empirical results.
Yes, yes.
That is true.
So when you plot the ratio of roughness with width, so this is basically like even for the deep network, it is just like you're multiplying. Let's say if L is the number of layers, you're just adding like L times R every time, right? So it is not like considering, okay, what if because this is what I was wondering, is it possible to get a different result? If you, for example, there might be some differences, for example, is only increasing the width of the first layer or the deepest layer, for example, something like that, some kind of experiments?
So I don't have numerics on it, but I can say that the trick is always the same. You consider the permutations of one of the hidden layers, then the next hidden layer, and so on, and they are multiplicative, basically. So the roughness that I'm showing would be different, but you can still compute this quantity for arbitrary widths.
And all networks you consider were MLPs, right? So only linear layers plus activations, right?
Yeah, but as long as the permutation symmetry applies, for example, for convolutional networks,
yes,
you can permute the filters, it's the same function.
They're still linear, and attention as well is still linear,
Thanks.
I have also one quick question. So in the end, I think the emphasis on the width, right? Sorry, the width and not necessarily the depth, because what we find is that if you increase the number of layers, for example, right, your average smoothness kind of becomes worse and worse. But it can also change with the initialization. So maybe it's not just the landscape, but a matter of how you navigate and where you start in the landscape as well. So if you consider this particular interplay, the depth, the width, and the initialization?
So one thing that I can explain with roughness is that, so if you're in the mildly overparameterized regime, the growing the depth makes the landscape harder. So that is one thing. But then there is the question of initialization and the dynamics. So maybe the landscape is super, super hard, but these hard objects are farther away, and the dynamics don't even go there. So this is, I'm not addressing that question here at all. But in an average case scenario, if I assume that these manifolds are equally distributed around the landscape, so there is some probability that you visit. So I think these are related to each other, but I'm certainly not claiming that this analysis is the answer of things. But I think there's a strong link.